Annualizing rates of return. There's two different rates we'll look at here. The first is APR, or annual percentage rate. Probably familiar with APR. I'm sure if you borrowed money out, you've certainly seen it before because lenders are required to disclose it to you when you borrow money. It's simply the per period rate. Multiplied by the number of periods in a year, number of compounding periods in a year. So on your mortgage, for example, if you have 12% mortgage, that means your APR is 12% and your per period rate is 1% per month. This rate ignores compounding. The effective annual rate, or EAR, is a more accurate measure of the effective rate that you're paying. So it's actual rate at which an investment grows, or the actual rate of interest that you're paying when you're borrowing money. Doesn't ignore compounding. So we can convert between the two rates. So, for example, we can calculate the EAR as 1 plus the APR divided by the number of compounding periods in a year. Multiplied by the number to the power of the number of compounding periods per year minus 1. We can convert back from APR to APR from EAR. So EAR plus 1 to the 1 over the n powers, and again, the n's the number of compounding periods per year, subtract 1 and multiply it by n. So this formula in the bracket, this calculates our periodic rate, and then we multiply it by the number of compounding periods per year, and we get we convert from our EAR back to APR. If you happen to be doing continuous compounding, it's simply, we're going to use E, which is 2.71, and a whole lot of other numbers after that. I'm sure your calculator has an E function. So E to the multiply, or to the power of the APR. So if you go back to our 12% mortgage example, it's E to the 0.12 minus 1 would give you the EAR for an APR. For to convert it back, the EAR back to an APR, you take the natural log of the EAR plus 1, and there is a natural log function on your calculator as well. There's also a function that will, on your calculator, that will calculate the EAR or APR for a given APR or EAR, whatever you're trying to convert. That's the iConversion function. Very simple to use, so you can check that out on your own. Next, we're going to talk about inflation and real rates of interest. So we have nominal rates and real interest rates. So nominal rate is this rate that you would see, this stated interest rate. And for the most part, when we're talking about nominal and real rates, we're talking about nominal rates, we're probably looking at treasuries, and then we're taking the difference between the nominal rate and inflation. We're going to talk about in just a minute the Fisher equation. This is effectively the derivation of the Fisher equation. So 1 plus the real interest rate is equal to 1 plus the nominal rate divided by 1 plus the inflation rate. For the most part here, what you're going to see with regard to inflation, we typically talk about this in terms of expected inflation. Example, so what's the real rate of return on an investment that earns a nominal 10% return during a period of 5% inflation? So 1 plus the nominal rate, 0.1, divided by 1 plus the inflation rate of 5%. So we have 1.048, so we subtract 1, so that's 0.048 or 4.8%. So Fisher equation. So the Fisher equation, basically, if we go back to this, you could you could rearrange this equation and have 1 plus r is equal to 1 plus capital R is equal to 1 plus lowercase r multiplied by 1 plus I. If you multiply those out, you'd have 1 plus r plus I plus RI. Well, RI is a really small number, so we can ignore that, and we can do an approximation with this formula. So nominal rate of interest is equal to the real rate of interest plus expected inflation. So yeah, EI equals current expected inflation. R nominal interest rate, R the lowercase r equals a real interest rate. So Figure 5.1 shows compares interest rates and inflation from 1926 to 2016. We don't really see that they don't show real interest rates here, but we can effectively calculate them or get an idea of what real interest rates were. You can see we had deflation in the 1930s and nominal interest rates there. Then in the late 30s and 40s, we had really high inflation and T-bill rates that were significantly below that right here. So we had negative real interest rates. We also had the same thing after the 2008 recession, because T-bill rates were effectively very close to zero, between 0.5% for much of that period, 2008 to 2016 period. So we again had negative real rates of interest. So T-bill investors actually lost purchasing power. It's a way to look at that. So U.S. history of interest rates, inflation, real interest rates. Since the 1950s, nominal rates have increased roughly in tandem with inflation, with the exception of a couple of periods. The worst case of that was after the 2008 recession. 30s and 40s, we saw the volatile inflation and negative real rates of return.